Okay. So, Michelson, Morley, Rydberg. Who are we looking at? All right, Michelson and Morley. Now, remember that 19th century classical mechanics, they thought light is a wave, like the ocean waves are waves. So, if it's a wave, it needs a medium. In the ocean, waves travel through the ocean. Sound travels through the air. Or, if you're underwater, it travels through water. So light, it's a wave, therefore it must have some medium. Now, when you're on Earth, that's not a problem. We have air and stuff. But they knew, even then, that outer space has to be a vacuum. They knew how gravity works, and they knew that matter would be attracted by planets, that it would have been, basically hoovered up by all the planets, and there would be nothing in outer space. So, in the 18th and 19th centuries, they resurrected the old, way old, like Aristotelian, ancient Greece kind of old, luminiferous ether. Well, actually, in ancient Greece, ether was just the fifth element, the quintessence. They thought, water, air, earth, fire, right, the four elements. They thought that outer space was made of a magical, non-earthly matter known as the ether. So being, classically educated in fancy educational institutions, these guys all knew about that. So they said, well, there must be this stuff called the ether, the luminiferous ether. It is the medium of outer space that allows light to travel. So Michelson and Morley decided to measure the luminiferous ether using the setup in the lower right. So here we have here's down here at A, we have this source of light, and then it gets bounced off of 5,000 mirrors. Now, they knew even then that light travels really, really fast. So in order to measure the speed of light in any sort of realistic way, you need to bounce it off of 5,000 mirrors. And then down here in the lower right, we have our detector. So, it's just traveling through. It travels through this lens in order to get narrowed down into a beam, then bounces off a mirror, bounces off a mirror, bounces off a mirror, just over and over and over again, bouncing off all these mirrors. So, the reason they're doing this is because the Earth is moving. If it's moving through space, then there should be some effect as it travels through the luminiferous ether, because it'll be moving through the ether in different directions at different times of year. And thus, essentially, they were looking for the wheom of as a car drives by you, the Doppler effect, more or less. Except instead of, the car driving by you, they're getting the slightly different version of the Doppler effect, where the car is where you're in the car, measuring a sound outside the car. You'll still get a Doppler effect. It'll still sound wheem, but it'll be kind of different. And that is essentially what they were doing. So, in another analogy that I totally stole from Bill Bryson's A Short History of Nearly Everything, Michelson and Morley held a hanky out the car window to see how fast the car was moving. Because, they were, moving through the ether. Basically, the Earth is moving in one direction in the spring, it's moving in a different direction in the fall. If you're measuring the speed of light in the spring, you should get a different measurement than you do in the fall, as it's moving in a different direction. They did not see that. Essentially, they proved very, very thoroughly that there is no luminiferous ether. The light travels at the same speed in all directions at all times. There is no ether. It does not need a medium. Outer space is the most absolute vacuum you can kind of see. So light is very, very different from other kinds of waves. It does not need a medium. There is no ocean for light. There is no, air for the light waves, okay, in outer space. Now, the next thing, before we talk about Rydberg, let's talk about line spectra. One of the things you might get to play with this semester is tubes full of gas. You take a tube, you fill it with a particular kind of gas, and you run energy through it, electricity. It'll give off light. but only a very specific kind of light. If you hold what's known as a spectrometer up to the sun, you'll see this top thing up here. Basically a continuous spectrum of all the colors of light. But when you run electricity through a pure element, you don't see that. You just see very specific lines. So with sodium, you get this line here in the orange, then a pair of lines here in sort of yellow-orange, another pair in this middle of yellow, and then another pair over here in green. For hydrogen, you get this one very specifically in red, another one in green, two more in blue. Calcium, a set of lines, but the point is, it's not really a spectrum. It is not this continuous set of waves that are all, just flowing from one end to the next. Instead, it is these very discrete, very specific, entirely separate lines, only individual frequencies. If you go in the other direction, these glasses will also absorb light. And again, only at those frequencies. So an emission spectrum is when it's giving off light, an absorption spectrum is when it's absorbing light. And people wondered why the elements do this. Why only those specific frequencies? So they spent some time looking around for these things. And what they found was eventually math. So hydrogen is a very, very well-behaved kind of gas. Remember, the lightest element out there. It had a number of spectra. So the first one that was discovered is here in the middle. It's known as the Balmer spectrum. It was the first one discovered because it's in the visible region. Then we have the Lyman spectrum over here in ultraviolet. Then we have the Paschal in ultra-red, and so on. So, Lyman in ultraviolet, Balmer in the visible, Paschen in infrared, Brackett in infrared, then Pfund, and then Humphreys, going further and further into infrared, then microwaves, and maybe, I guess, out into even radio waves. Go far enough. But it had these various spectra. Now, the reason that these all have people they're named after is because those people, Lyman, Balmer, Paschen, etc., came up with these guys here. What they are is mathematical formulas describing those spectra. What they noticed is that if you take 1 over the wavelength, you can compare it to a mathematical formula based on integers. So here we have Lyman. Here is the lowest frequency, or the longest wavelength in his spectrum, and then a series of lines after that for different wavelengths. And for each one of those, you have 1 over the wavelength is equal to this constant multiplied by 1 minus 1 over n squared, where n is some integer greater than 1. So 1 over 2 squared, 1 over 3 squared, 1 over 4 squared. So 1 over 2 squared, 1 over 3 squared, 1 over 4 squared, 1 over 5 squared, and so on. And then Balmer found almost the exact same thing. 1 over the wavelength, same constant, but instead of 1 minus 1 over n squared, it's 1 over 2 squared minus 1 over n squared, where n is greater than 2. So 1 over 3 squared, 1 over 4 squared, 1 over 5 squared, 6 squared, 7 squared, and so on. Paschen, same thing, 1 over the wavelength, same constant, 1 over 3 squared minus 1 over n squared, where n is greater than 3. Brackett, same sort of formula, but 1 over 4 squared minus 1 over n squared. Pfund, 1 over 5 squared minus 1 over n squared. Humphreys, 1 over 6 squared minus 1 over n squared. So each one of them found a particular set of lines and noticed this exact same mathematical pattern. 1 over a constant squared times minus 1 over n squared. So in this case, for Lyman, it's 1 over 1 squared, or just 1. Now, Rydberg comes in because he noticed a trend. He noticed this habit, the way these things are all behaving, and he put them all together in what's known as the Rydberg equation. 1 over the wavelength is equal to a constant that we now call the Rydberg constant, multiplied by 1 over n1 squared minus 1 over n2 squared. So the Rydberg constant, 1.097 times 10 to the negative 2 inverse nanometers. That way you get nanometers for the wavelength. And then you have these two integers. N1 is any integer, 1, 2, 3, 4, etc. Any positive integer, I should say. And then N2 is any positive integer greater than N1, so 2, 3, 4, 5, etc. And thus, using this more general equation, you can recreate all of these equations and thus create any spectrum you care to name for the whatchamacallit for hydrogen. Okay. So that is the Rydberg equation. He became, he is now famous throughout history because we're always going to teach this in chemistry classes as they lead up to quantum mechanics. So here's a question. Why does hydrogen care about integers? Okay, hydrogen it's an atom. It's an element. It's a proton and an electron. It's unthinking matter. It's not a little nerd sitting there with a pocket protector and a calculator saying, I like numbers. 3 is my favorite number because it makes triangles. No, it's an unthinking bit of matter. Why does it care about integers? Okay. So that is the Rydberg equation, and that presented physicists with a mystery. And we'll leave it there for the moment. We'll answer that question in the next set of slides. First, we have mathematical problems. These are examples of very basic math problems that you could see on a test. These are based on these mathematical things down here on the bottom. First, on the left, we have C equals lambda nu. This is the Greek letter lambda, and we use that to represent wavelength. And then this is not the letter V, plebeian. That is the letter nu, Greek letter nu. It's a swoopy looking V, and we use that for frequency. C is the speed of light. That's a constant in a vacuum. 2.998 times 10 to the 8th meters per second. Or 299.8 million meters per second. It moves very, very quickly. So wavelength and frequency for light are always tied together. Okay. So one thing they could ask you to do on a test is they could give you a wavelength, ask you to find a frequency, and then the exact same way they could give you a frequency and ask you to find a wavelength. Okay. So real quick, I'll go ahead and walk through those problems. Also here on the right, we have the Rydberg equation. 1 over lambda, 1 over the wavelength, is equal to the Rydberg constant times 1 over n squared minus 1 over m squared, where n and m are two different constants. So let's go ahead and walk through these problems. Okay. Grabbing a random, okay, purple. We're going with purple. So let me bring up, boop, there's the paper. All right. Okay. So what is the frequency of light at wavelength 867.7 nanometers? All right, so, well, before you can do these problems, you have to remember you need your units in the same units. Thank you. So C is equal to 2.998 times 10 to the 8th meters per second. So if we're going to get frequency, we're going to need to translate from nanometers to meters. Okay. So just a real quick way to do that, 867.7 times 10 to the negative 9th meters. Okay. Because remember, nano means 10 to the negative 9th. Okay. So that is just the easy way to do it. Then when you put that into scientific notation, 8.677 times 10 to the negative 7th meters. Okay. All right, so C equals lambda nu. So this is what we're solving for. We have our wavelength and we have the speed of light. So nu is equal to C divided by lambda is equal to 2.998 times 10 to the 8th meters per second divided by 8.677 times 10 to the negative 7th meters. All right. Where? Dang it, my scientific calculator's out in the car. So I'm just going to go ahead and use the crappy calculator provided me by thing. All right, by Windows. So here comes my calculator, scientific calculator. So 8 10 to the 8th times 2.998. So there is the speed of light, 299,800,000 meters per second, divided by, let's go ahead and put it in parentheses, 8.677 times 7 negative 10 to the close parentheses equals a very, very large number. Okay, so that is 3.4, see, 4 sig figs, 5 times 10 to the, I'm guessing it's going to be 14th per second. Okay, so meters cancels, leaves you with per second, aka inverse seconds, aka hertz. Okay. So let me double check that that's 14, 3, 6, 9, 12, 13, 14. Yes. Okay. I was able to get that because 7 and 8 adds up to 15. Then it's 3 divided by 8, so it's going to go down by 1. Again, that's just the sort of intuition that you build up if you practice lots and lots of math. Let's see if I can't make this a touch smaller. Yes, good. All right, so that is how you would calculate frequency from wavelength. Okay. So let's move on to the next problem. Let's bring back up this guy here. Let's close this real quick. All right, what is the wavelength of light if it has a frequency of 1.768 times 10 to the 15th hertz? Okay, exactly the same sort of problem, only instead of calculating wavelength, we are calculating, or instead of calculating frequency, we're calculating wavelength. So exactly the same sort of problem. You'd solve it in exactly the same way. Okay, C equals lambda nu, so lambda equals C over nu. So it's going to be 2.998 times 10 to the 8th meters per second divided by 1.768 times 10 to the 15th hertz. Do you have to do anything for the units? Not really, because hertz is the same thing as per seconds. So the per seconds and the hertz cancel out. And all you have to do is 2.998 times 10 to the 8th divided by 1.768 times 10 to the 15th. Okay. Or 10 to the negative 7th, and then it's just 2.998 divided by 1.768. Okay. So that's what I'm going to put in the calculator. So let me bring that back up. 2.998 divided by 1.768 gets us 1.696 times 10 to the negative 7th meters, or we move this 2 to the right, 169.6 times 10 to the negative 9th meters, or 169.6 nanometers. Meaning that this is in the far ultraviolet, or maybe not far ultraviolet. I know it is ultraviolet, because visible light goes from about 700 nanometers for red to 400 nanometers for blue. So 169.6 nanometers, that is on the far side of blue. So it's somewhere in ultraviolet probably. All right, moving back to the problems that we have here. What is the wavelength of your radio station? Magic 98.9. So this is FM, meaning frequency modulated. So 98.9 means 98.9 megahertz. So again, this is just a C equals lambda nu problem. What is the wavelength? All right, so 98.9 megahertz. Well, mega means 10 to the sixth. That is very difficult to see. Sorry about that. But that means 98.9 times 10 to the sixth hertz, or 9.89 times 10 to the fifth hertz. Okay. Wait, do I have that right? No, it's 10 to the seventh. Okay. All right. Excuse me. So it's times 10 to the seventh, not times 10 to the fifth. All right. So C equals lambda nu, which means lambda equals C over nu. 2.998 times 10 to the eighth meters per second divided by 9.89 times 10 to the seventh per second. Hertz is just per second, or 1 over second. So the per seconds will cancel, leaving us with something on the order of a meter, something very close to 1 meter. 2.998 divided by 9.89. So we're going to end up with 3 sig figs equals 0.303 times 10 to the first meters, or 3.03 meters. Okay. Meaning for a typical radio station, their wavelength is going to be on the order of a meter, or to 10 meters, maybe down to a centimeter, or 10 centimeters, excuse me. Wavelengths are very long for radio waves, whereas they're very, very short for visible light. All right, so final problem. Oops. Bring that back up, throw that away. What is the wavelength of light emitted by hydrogen for integers 2 and 7? What is the frequency? And is it visible light? Okay, brown. That's different. So now we're going to be using the Rydberg equation right here. So, okay, so the Rydberg equation, 1 over lambda is equal to the Rydberg constant, RH. So that's 1.0973 times 10 to the seventh inverse meters, times our two integers are 2 and 7. The first one has to be the smaller integer, so that's going to be 1 over 2 squared. And the second one is our larger integer, so 1 over 7 squared. So those are the numbers we plug into our calculator. Let's go ahead and do a bit more work. 1.0973 times 10 to the seventh per meter. 1/4 minus 1 over 49. All right. So open up our calculator, right quick. 1 divided by 4 minus 1 divided by 49. So 0.22959 ... Those are integers, so they're exact numbers. So they have infinite sig figs, more or less. So our answer is going to be limited to the 5 significant figures that I provided for Rydberg. So we go ahead and we multiply that by Rydberg. 10973. That's 1, 2, 3, 4, 5, 6, 7. All right. 10,973,000 per meter. All right, meaning that 1 over lambda is 2,519,300 per meter. So that is 1 over lambda. So that is not the wavelength. That is the inverse wavelength in per meters. Okay. So in order to solve it, you need to solve for lambda. So lambda equals 1 over 2519300. Okay. So it's just 1 over our answer. Do we have a button for that on this calculator? We do. So that is 3.9693 times 10 to the negative 7th meters. Or 396.93 times 10 to the negative 9th meters, or 396.93 nanometers, which is just barely at the edge of visible light. I don't know if it would be visible or not. The 700 to 400 nanometer scale for red to blue, that is a rough guideline. And of course, it's going to vary from person to person, depending on their eyes, how good they are, how damaged they might have been by a life spent looking at the sun, things like that. So that would be right there at the very edge of the visible light spectrum. Maybe visible, maybe not, depends on the person. Okay. Oh wait, I forgot the frequency. So the frequency, nu is equal to c over lambda. So that's going to be 2.998 times 10 to the 8th meters divided by 3.9693 times 10 to the negative 7th meters. Going to be something times 10 to the 14th. So 2.998 divided by 3.9693 equals 0.7553 times 10 to the 15th hertz, or 7.553 times 10 to the 14th hertz. All right, and those are the 4 problems that I made up for this particular set of questions. I don't know for certain that they will throw, I mean, they probably wouldn't ask you about a particular radio station that actually exists in Greenville. They wouldn't necessarily throw those 2 integers at you, but those are examples of the kinds of problems you might see on a test. They will almost certainly ask you to convert between wavelength and frequency, and they'll very, very likely throw a Rydberg problem at you. All right. And I believe, yep, that is it for this particular set of slides. Yep, I will go ahead and do one more set of slides tonight, Planck and Einstein, and I will be back for that in